Now we're going to talk about section 4.5, the real zeros of a polynomial function. Not the real zeros, the real number zeros. Let's say that we have a function, f of x equals x to the fifth minus 5x to the fourth plus 12x cubed minus 24x squared plus 32x minus 16. And let's say that we had to find f of 4, or find the x-intercepts, which would mean setting this entire function equal to 0, and then trying to solve it, perhaps by factoring? What else could we do? It might actually be totally impossible using the methods that we've learned how to factor. Also, to find f of 4, you'd have to take this 4 and plug it into each one of these terms. Yeah? I don't know about you, but sometimes when I plug numbers into big, long polynomials and do a lot of computation, I make mistakes. So both of these tasks, if I had to do with this big, long polynomial, I say yuck. Well, in this section we're going to learn about two theorems that are so awesome that you'll love them forever, I promise. The first one is called the remainder theorem. It says, let f be a polynomial function. If that polynomial function, f of x, is divided by a factor, x minus c, then the remainder is the value of f of c. So what we're saying is then is that if we wanted to find f of 4, we divide f of x by x minus 4 and take the remainder. Yeah. Does it seem like magic? Well, take a look. Why does this work? Well, I want you to recall something before I show you the proof of this theorem. If we were to take the number 312 and divide it by 14, I could use long division. Remember this from when you were much younger. 312 divided by 14. 14 goes into 31 2 times. 2 times 14 is 28. We subtract, we get 3, bring down the 2. 14 goes into 32 another 2 times. Subtract 28, and that leaves me with 4. The remainder 4, right? This information can be summarized in a couple of ways. We could say 312 divided by 14 equals 22. That's our quotient, and the remainder 4 over 14, right? Or, oops, sorry, stop it. I can take 312 over 14, which also means divide. I get 22 plus 4 14ths, which is exactly what 22 and 4 14ths means. Or I can also write that statement this way. If I multiply both sides of this equation here by 14, I get 312 equals 22 times 14 and then plus 4, right? Because if I multiplied by 14 here, it would cancel out, it would clear the fractions, and then of course leave me with 22 times 14. So this number in my division is called the dividend. It's the number that we're dividing. This number here is called the sorry, that's not right. It's called the quotient. Quotient. This number here is called the divisor. That's what we divided by. And 4 is the remainder. Okay? So, remember that? All right, now we're ready to do the proof. Remember what we're trying to prove. We're going to show that if f is a polynomial function and we divide it by x minus c, then the remainder is the same thing we get for f of c. So here we go. Here's our proof. So because of what I just described with numbers, if we take f of x, right, if we divide f of x by x minus c, we get a quotient, which will be another polynomial, q of x, and a remainder, r. Yeah. We end up getting this. F of x equaling the divisor times the quotient plus the remainder. Remember what we said up here? We have the dividend equals the quotient times the divisor plus the remainder. So here we have the dividend, the thing we're dividing, the quotient times the divisor plus the remainder. So my original function, when I divide it by x minus c, can now be written this way. Now let's find f of c. Well, basically that says take my f of x, which is right here now, and plug in c everywhere I see an x. So I get c minus c times q of x plus r. Well, c minus c is 0. So 0 times q of x plus r equals 0 plus r, or just r. So notice we get f of c equaling r, which is the remainder. Right? All right, pretty cool. But we don't want to have to do polynomial long division like we did long division with the numbers up here. Yuck. So what we're going to do instead is we're going to use what we call synthetic division. So you may have done this before, or maybe not. I'm going to review it pretty quickly. There are other videos in the book that show you exactly how to do this if it's not clear from my video. So f of x, if I'm going to divide f of x equals x to the 5th minus 5x to the 4th plus 12x cubed minus 24x squared plus 32x minus 16, using synthetic division, by x minus 4, this is what we're going to do. We'll take the 4 from here, we'll put in a division sign, and now I'm going to write the coefficients of each one of my terms. So I get 1, negative 5, 12, negative 24, 32, and negative 16. Okay? I draw a line here, and we do this. First thing we do is bring down the very first coefficient, 1. We multiply 1 times 4 to get 4. Now I add negative 5 and 4 to get a negative 1. I repeat that process over again. I multiply negative 1 times 4, which is 4. I'm sorry, negative 4. I add 12 and negative 4, which gives me 8. I take 8 times 4, which is 32. I add negative 24 and 32 to get 8. 8 times 4 is again 32. I add 32 and 32 to get 64. And then 64 times 4 is 256. And when I add negative 16 and 256, I get 240. Anytime we use synthetic division, this number right here is our remainder. If you want to check it by doing polynomial long division, be my guest, but you will get 240 as a remainder. Now remember what the remainder theorem told us. If we divide a polynomial times a factor x minus 4, the remainder gives us that value at f of 4. So now I can say f of 4 is equal to 240. Yeah. Believe it? Well, let me show you. Let's take our original polynomial and find f of 4 by plugging in 4 instead of using synthetic division. So we get 4 to the 5th minus 5 times 4 to the 4th plus 12 times 4 cubed minus 24 times 4 squared plus 32 times 4 minus 16. Okay. As I evaluate these things, I get 1024 minus 1280 plus 12 times 64 is 768. 24 times 16 minus 384. 34 times I'm sorry, 32 times 4 is 128, and I subtract 16. And if we put all these together, we get 240. You can check the math, but it does work out. But notice how yucky it is to have to take 4 to the 4th, 4 to the 3rd, 4 squared, then 4, then plug it in, then do all this addition and subtraction, when we could get there simply by doing this very simple process of synthetic division. Alright, so what, right? Well, when we use the remainder theorem in conjunction with the next theorem I'm going to show you, it helps us factor big polynomials, meaning polynomials of high degree. Why would we ever want to do that, right? Well, if we can factor a big polynomial, we can then set each factor equal to 0 to find the zeros of the polynomial. And also, we'll be able to, which will help us to be able to graph. And start to graph it. All right. We're going to notice something before I give you that next theorem. We're going to notice that if c is a 0 of f of x, this means that f of c equals 0, right? How do we know that? Well, by saying f of c equals 0, then we know that the point c, comma 0, c is the x, 0 is the y, is on the graph of f, right? And where does c0 occur? Well, it occurs right here at c on the x-axis. Hence, c is a 0 of that function. However it's going, oops, however it's going through there, right? So, if f of c equals 0, then by the remainder theorem that we just talked about, if we divide f of x by x minus c, then we will get the remainder of 0, right? So notice, if I divide by x minus c, right, and I get a remainder 0, right? I'm going to get some other factors here. I don't know how many there are. But I'm going to get plus 0, meaning there's no remainder. And if that happens, then f is fully factored. So again, we're going to be able to factor by using the next thing, which is cleverly called the factor theorem. The factor theorem says, let f be a polynomial function then x minus c is a factor of f of x if and only if f of c gives us 0. All right? And to find f of c equaling 0, we can use synthetic division and the remainder theorem to prove or to factor. Okay? Are we ready to factor f of x or solve f of x equals 0? Well, not yet. We can use the factor theorem to prove that things are factors, but how do we know what to try? All right? In the next video, I'll show you how to do that.